In this lesson, we're going to talk a little bit about an idea we first introduced back in pre-calc, which is continuity, which means whether or not a function is continuous. And we're going to also work in an idea we've been working with all year pretty much in this course, which is the idea of differentiability, which just means the derivative exists. So to introduce these two ideas and their relationship, we're going to think a little bit about roller coasters. So you're going to be on your senior trip soon enough to Six Flags. Imagine in this scenario, you've been asked to review each of these roller coasters for safety. And one roller coaster is safe, one's like a little bit sketchy, and one is you would die, right? So pretty obviously, like my nice smooth curve in the middle is safe. This one with the big hole in it is probably deadly. And then this one with the little sharp point right here is like a little bit sketchy. You might crash. You probably will crash. Okay? So what we need here is some mathematical ways to describe these properties so that we can then apply them to things like this analytic function that we have here on the next page. So I would describe my safe roller coaster as both continuous, I can draw it without picking up my pencil, and I would describe it as differentiable, meaning the derivative exists everywhere along the curve. I would describe my deadly coaster as neither continuous nor differentiable at x equals 1. So that hole there, obviously not continuous, there's a jump discontinuity, and it doesn't make sense either to talk about the derivative because the derivative is different depending on which piece of the function I'm on. And then my kind of sketchy but not deadly coaster, I would say this is continuous everywhere, right? Because even at that sketchy point, I don't have to pick up my pencil, but not differentiable at x equals -2. Okay, and the reason it doesn't make sense to talk about the derivative there is my slope from the left is positive, my slope from the right is negative, right? So imagine I was trying to draw the tangent line to the curve at x equals -2. I wouldn't know which way to point my line. So that is essentially the intuition behind this lesson, is the difference between like totally crazy deadly versus sketchy versus perfectly safe roller coasters. However, it can't be that easy, right? So what we're going to start to do is describe these using limit statements. So limits are the building blocks of calculus here. And we're going to use this notation, this mathematical notation, to describe each of these properties. So to show that my first coaster is deadly, by the way, instead of deadly now, we're going to say not continuous. I'm going to say my limit as x approaches 1 from the left of f of x is not equal to the limit as x approaches 1 from the right. Okay, so we did this in pre-calc, and all we're really saying by this, right, is that as I walk along the roller coaster from the left of 1 versus when I walk along the roller coaster from the right of 1, I end up at two different spots, right? So in words, I would say that the left and right pieces of this function don't approach the same value. That's what I'm saying here. So this is a proof that the function is not continuous. Here, we have a different function, different roller coaster. This one probably wouldn't even work in real life, even if it didn't have that hole in it. But that hole there makes it not continuous. Okay? Here, I can say, first of all, that my limits are equal. So I could say the limit as x approaches this value is 2 from the left is equal to the limit from the right, but the limit as x approaches 2 is not equal to f of 2. Okay, so we have a three-part definition of continuity, and that is my left limit has to be equal to my right limit, has to be equal to f of x. And this last part, right, says we can't have a hole in my graph. So I can't have maybe a dot up here, or I can't have just like this open circle. I need all three of these things to be the same to make a continuous safe roller coaster. Okay, then my last statement here, show using limit statements that my coaster is continuous but not differentiable. So this is really going to lay the foundation for the types of problems we're going to be solving on the next page. So look at this point at x equals -2. I'm going to say here, for my proof of continuity, that my limit as x approaches -2 from the left of f of x is equal to my limit as x approaches -2 from the right is equal to f of -2. And just to be clear, it's for all day, right? So as I walk towards that point from the left versus from the point versus just if I go straight there, I get 4, 4, 4. Continuous wrong. So I can say, so f is continuous at x equals -2. And then I'm asked to show that the function is not differentiable. So again, I'm going to use a limit statement. But here I'm going to talk about f prime of x, right? So remember what we said is that my slope from the left was positive. My slope from the right was negative, right? So the way I show that the function is not differentiable is I say the limit as x approaches -2 from the left, this time of f prime of x, is not equal to the limit as x approaches -2 from the right of f prime of x. So this shows that the function is not differentiable. My slopes are different on both sides. It doesn't make sense to talk about the slope of the curve at that point. Okay, so this is the intuition behind what we're doing. Other than the mathematical notation, the ideas are simple. And the ideas, again, are deadly safe for sketchy roller coasters. All right, so here we're going to tackle this idea algebraically, determine whether f is continuous and differentiable at x equals -1. And notice that's the point where our two pieces meet up. And then we're asked to justify our answer, as we often are asked to do so in AP Calculus. So I'm going to do exactly what we talked about on the previous page. So for continuity, I'm going to take my left limit, my limit, as x approaches -1 from the left of f of x. And that's going to be my top piece, my less than -1 piece, which is 2 times the natural log of -x. It's 4. And to solve this limit, I just plug in. Natural log of 1 is 0, because anything to the 0 power is 1. So I get -4. So there's my left limit. My right limit is going to be equal to the limit as x approaches 1 of my other piece, which is -x squared minus 3, which if I'm plugging in -1 would be -1 minus 3, which is -4. And then f of -1 would also be -4, because it would just be the same as this. So then I could conclude that f is continuous at x equals -4 because I have f of -1, my left limit, and my right limit all equal to 4. So I'd say yes for continuity. Now the second part of my question was differentiability. So to do this, we need to examine the derivative of f prime. And to do that, I just use my derivatives rule. So this one easier, -2x, right, power rule. And then here, the derivative of log of -x is 1 over -x. The 2 is outside, and then the negative in the red is chain rule. Okay, and then I'm just checking to see if both sides are equal, right? So I can say the limit as x approaches -1 from the left of f prime of x is equal to what I get when I plug in -1, which is -2 over -1, which looks to me like it is -2. And the limit as x approaches -1 from the right of f prime of x is equal to just -2 times -1, which is equal to 2. Okay, so notice these things are obviously not the same, right? So I'd say f is not differentiable, because what we just showed, right, is that we have a sketchy sharp point in our roller coaster.